Hello, thank you all for joining us today for the continuation of our Uplink Management Best Practices series. We'll begin in just a minute or two. All right, thank you again for joining today's session, Managing PIM in Your Radios. My name is Natalie Camero with Viavi. Before I introduce our speakers, I'd like to share with you some housekeeping tips. The session today is being recorded and will be available for sharing in a few days. All lines are muted, but questions are welcome. To ask a question, please use the Q&A option at the bottom of your screen. We'll also have a short survey at the end, and we appreciate your feedback. Now, to introduce our speakers today, we're pleased to have Tom Bale, Executive Vice President of Product Line Management from ConcealFab, where he leads a team to develop solutions to mitigate external passive intermodulation at cell sites. Prior to joining ConcealFab, Tom spent 6 years working in the PIM test equipment industry as a product manager and 15 years in the base station antenna manufacturing industry in a variety of roles, from engineering to sales. From Viavi, we have Eduardo Insunza, Product Line Manager, and Dan Schmecci, Domain Solutions Expert. Eduardo has been in the test and measurement arena for more than 25 years and has been with Viavi for over 11 years with deep technical knowledge and field expert experience. Dan Schmecci provides sales support and wireless technology expertise. He's been with Viavi for more than 13 years, and prior to that, he had experience as an applications engineer, systems engineer, and national account manager for 2 major U.S. service providers. We're pleased to have this combined knowledge to share with you today. I'll turn this over to Eduardo, who will lead the session. Eduardo?
Thank you, Natalie, and hello, everyone. So in this session for uplink interference PIM detection, we're going to be starting just with a brief overview. This is not going to be a repeat of the previous webinar that we had, but it's important just to highlight a couple of important aspects about PIM. And then we're going to be talking about the RF receiver or PIM detection on new radios. And that's when radios are handling multiple bands or multiple carriers and the challenges that we face on them. And then we're going to have a brief PIM detection demo. And at the end, we're going to be closing out with a PIM mitigation best practices. So as Natalie said, please feel free to ask us any questions and we'll try to answer them all. So let's start with PIM. And again, with the understanding that we all know that PIM it's created with an improper kind of conductive characteristics of a medium. And in this specific example, I'm just showing how a single carrier that, by the way, this is just an LTE example, has multiple subcarriers. And if when they go through that kind of not linear conductive medium, PIM is created, and it's created among the different subcarriers. And as an example, subcarrier 0 and subcarrier 599, because this is just a 10 meg signal, it happens to be landing on almost the center frequency of the uplink. But in any case, this is just to give you a sense on how the PIM signature looks like when we have an OFDMA signal, which it's all LTE and 5G signals. Now, all the transmission that is happening right now with 5G in C-band or mid-band, that is everything above 3 gigahertz, it's TDD based. So that means time division duplex. And previously it was kind of the conception of, does it exist PIM in 5G mid-band TDD signal? Yes, it does. Is it going to be hitting my 5G signal? Maybe not, unless there are adjacent carriers that might be affecting with a different frame configuration. However, though, if we're collocating the 5G with LTE, as a result, we're going to have multiple combinations of different radio types that might be affecting or might be impacting my 5G signal. So it's important to really understand and make all these different radio certifications and PIM testing just to make sure that there's no PIM hitting into 5G. Now, as I mentioned before, this is as an example of a PIM signature. So all the tests that we do for PIM detection are through the CPRI link. So we just put an optical splitter and we just take a sample. The radio, it's still ongoing, it's still servicing. Sometimes there's some synthetic low generation type of channel being enabled. So the PIM, it's there, it's excited, and we have power hitting on the uplink noise floor. In this specific example, as you can see, we have just one carrier, 4 MIMO branches, and all of them are being hit or impacted by PIM. So again, this is just a recap of how we are analyzing and how a PIM signature looks like. Right, now, there are different ways in which we can analyze PIM, and we can differentiate different branches. So in this example, on the left-hand side, you see a couple of spectrums. Actually, those are coming from the same carrier, but 2 different MIMO branches. One happens to be clean. As you can see, it's pretty flat, the uplink, so there's no PIM being impacted. However, on the other antenna, which it happens to be in this example, the PIM on antenna number 4, it's called RX3, but in any case, you have 0, 1, 2, 3 or 1, 2, 3, 4, but clearly here we can see that only one of the antennas are being impacted by PIM. Right, so I'm going to spend just a few more time here because it's important to understand a couple of aspects, and those aspects actually are going to be creating some challenges for 5G, or for that matter, for any new radios. And let me just briefly describe a new radio. New radio, it's those that are handling multiple carriers or multiple bands. So we have low, low, high, high as an example. There are single band multiple carriers, but also we have dual band or tri-band with multiple carriers. Now, how is that impact the PIM detection capability? So let me just go through, again, some of the basic process that happens between the BBU and the remote radio head when a signal is being created, and then how is being sampled. And as you can see here, we have multiple options on how the signal is being sampled. As an example, here we have a downlink that can be sampled between 8 and 20 bits, in the uplink 40 to 20. So everything is standardized and it's fine. However, we have different options in which we can do it. So then we can map all these IQ sample bits, and we group them because the AXE containers can handle 3.5 megahertz. So we're carrying over a 5, 10, 15, 20 megahertz carriers. We have to have multiple of these AXE containers. So we are grouping them. Now, let me just make one step backwards. So the AXE containers, as you can see the values, we have multiple values. And then, as I said, each one of them, it's 3.5. So we can have multiple of them, 4, 6, 8, 12, so on. And based upon the carrier that we're transmitting, we're going to be choosing those different values. But as you can see here, there's several values available. Now, when we group an AXE container, is being transmitted, and this can be fixed, or it can be floated or packed. So that's also kind of an option that we have. And when we do so, then everything is basically put on a hyperframe and is being transmitted out. So anyway, this is the whole process. And as you can imagine, we have a BBU that is handling all the signal processing, and everything is baseband, meaning that everything is digital. Now, everything, all the signal, when it's mapped and put on a CPRI packet, is being sent to the remote radio head. That's the one that makes the conversion from digital to analog, in this case, going from downlink, takes that signal, amplify it, put it on a specific carrier, and transmits that signal out. Similarly, it's in the opposite direction on the uplink. So here, as we can see, we have different mapping. Just to summarize, even though we have multiple options, in reality, it can be done very easily with the one advisor. This is just the test equipment that we have that makes all these testing and analysis of RF over CPRI. And even though we have all these different variables defined by the standard, we certainly can manage all of that. So in this example, we see the entire CPRI word and all the space or the bandwidth that we have available. On the right-hand side, you have I'm pointing here into the RF mapping. So that basically also is all the data, all the IQ data that is being transmitted out. On the left-hand side is just the overhead. But it is very important that we have the ability to handle all these different values or variants that the standard allows us to do, because as it happens, multiple network element manufacturers, they're taking or considering different ways to map IQ into CPRI. So it's really important to have these flexible configurations so we can select different IQ sample widths, for example, different stuffing bits, exponent bits, and so on and so forth. So this is really, really important. Now, RF over CPRI new radios. As I mentioned before, typically we have a BBU of CPRI over fiber and the remote radio head. And just as the example or the process that I described before, the BBU does all the signal processing, modulation, the digital IQ components, put it in a sequence, and that sequence basically is put on this packet that is being transmitted out. Now, the remote radio head then takes all that, makes the conversion, as I mentioned before, from digital to analog, put it on a carrier, amplify it, and sends that over. And as you can, it's exactly the same process if it's downlink or uplink. So it's important to make that distinction. Then when we're making a test, an uplink PIM detection test, this is the reason why everything is baseband, because the radio has processed already that signal, is not an analog, but a digital signal, and that's what we're analyzing. So as an example of a multi-carrier or multi-band, let's make the assumption that here we can have, as I said, say a single carrier. In a case A is one carrier, we have a 20 megahertz, and it has 4 branches. Okay, so total we have an 80 megahertz bandwidth. Now, there are some other combinations that we have, for example, a new radio, and here I just have a few examples in cases B, C, and D. As you can see here, this is a dual carrier radio. And in these, similarly, we have channel 10 megahertz for 2 carriers, MIMO 4 branches, same bandwidth. Or other combinations, case C, for example, we have a 20 megahertz signal with 2 branches and a 10 megahertz signal with 4 branches. Or case D, it's a 22 branches, 22 branches. So in any case, as you can see, all of them are showing the same total bandwidth of 80 megahertz. This is just as an example, but as you can imagine, there are some other combinations. If you add 15 and 5 megahertz signals. The point that I want to make here is that with all these different configurations, we can have the same data block. So it's from a digital perspective, it's exactly the same. It's 80 megahertz, but we don't know how all those carriers are being transmitted or accommodated because everything is digital. So this is one of the challenges that we have, that in new radios, we're going to have multiple carriers, and it's not very clear which carrier is which. For example, if we have an external interference, and in that external interference, we have a problem, and we want to identify in which frequency that external interference is being shown, then we don't know, right? Because we don't know exactly which carrier we're analyzing. Similarly with PIM detection, we're having PIM, let's make the assumption that we have case B. We have 2 10 megahertz signals. We have all these 4 branches for each one of them. We're analyzing, we're saying, yep, we see PIM in one of the carriers, but that information of which carrier it is not available. So how we're solving this problem or this challenge, the way in which we're solving this problem is by having a frequency reference available. And that frequency reference is at the same time that we're analyzing CPRI, we're injecting a tone, an RF tone. So in this example, we're sending out a tone on that frequency of one of the carriers. And if that is being shown on the uplink, that is basically how we can identify different carriers. So this is really important that at the same time we can do it so we can have the certainty on the frequency that we are analyzing. Now, this is kind of the second challenge that we have as I briefly described in the process of how an analog signal is being kind of converted and mapped into the CPRI packet or CPRI frame. Here's one example that, as you can see, all the data is being distributed across the entire world, as well as is floating. So there's a gap between each of the RF components. This is another example. It's packed, is not distributed. As you can see, it's at the end of the word, of the CPRI word, that is. And we have some reserved bits between each of those packets. This is another example. As you can see, it's packed. Starts with one carrier. There's a gap. And then there's another frame or another carrier. And everything is consecutive, meaning that they don't have any reserved bits between the groups.
Eduardo, may I jump in here for 1 second?
Sure.
Yeah, on the previous slide, guys, I want to elaborate why we're talking about this. Eduardo did a very nice thing and didn't give you the vendors. But there are 3 different vendors. This is North America we're talking about here. Each one of the 3 is represented on this slide deck. And the reason we show it is, whoever your vendor is. And when I say vendors, the equipment manufacturers, the Ericssons of the world and the Nokias and so on. This allows the end user, all of us, to quickly identify, okay, here's where this baseband data we talked about earlier is, and set up config files and or auto config to these. And they, again, each vendor is drastically different. And for those who've played with our tools or any tools out in the market, you know that, but we wanted to make sure we start talking about the differences in configuration and just making sure you guys understand that it's flexible enough to cover them all. Thanks, Eduardo.
Thank you, Dan. So let me just continue with kind of some other examples that we've seen in this this middle example that I'm showing right there is packed, is consecutive, but as you can see, these two different carriers, actually there are three of them, but they're just showing here two, the one in the middle and the one at the end. But again, all the data, it's at the beginning of the word, everything's packed and consecutive. This is the last example set that I want to show you. In this specific one, and there's an intermix. As you can see, it's at the end, it's packed, reserved, but the antenna branches are mixed, which, and again, it's a kind of a different twist. And this is the last one. This is a bit more complex. Actually, there are three different carriers here, but as you can see, we have a gap between them. It's packed, reserved, and so on. So in any case, all these different examples that I'm showing here, just to highlight that everything is changing, and everything also, to be honest, will continue to change. It's all the data, all the super data being transmitted on one fiber or on two fibers. That is also being addressed. Sometimes, most of the times, is one fiber, sometimes is two fibers. So again, there's just too many variables, and to properly address all those variables, we have the ability, or we have implemented the ability to basically address all those different options or variants that the CPRI standard defines. By doing so, we're going to be able to properly, effectively identify all these different variants of new radios, and that's really key, and that's really important. And once we do that, as Dan mentioned, certainly automation can be achieved. But the first and most crucial aspect of it is that to have the ability to have all the configuration available, so we can do so properly. And the other aspect, the challenge that I mentioned, is the ability to have an RF source or RF reference with which we're going to be able to identify different carriers being transmitted out. Now, there's one more thing that I wanted to point out. Typically, management systems report PRB. This is just one example on a heat map of PRB. What is a PRB? It's a physical resource block. How it's defined. So we have here a carrier, we have frequency and power. Actually, it has multiple subcarriers, as I mentioned before. Now, if we kind of put kind of the time axis on it, we see kind of all my subcarriers and all my symbols. And as it happens, according to the standard, a resource block or physical resource block is this matrix of 12 subcarriers by 7 symbols. This is specific for LTE. In 5G, it's a slightly different, same concept, but it's a 12 by 14 symbols. But in any case, what is a PRB from a frequency standpoint? Is basically these 12 subcarriers multiplied by the subcarrier spacing, which in LTE, it's always 15 kilohertz. Therefore, each PRB is 180 kilohertz wide. So in this example, we're seeing kind of a signal right in the center of it. It's about 10 PRBs, so that's as wide as 1.8 megahertz. So anyway, so when we are gonna analyze a signal and the management system is giving us this information, that most likely it's around PRB 19 to 28. That's 10 PRBs is 1.8. How can I translate that into frequency? So one of the things that we have implemented is then not only to look into a frequency, but also look into a PRB table. So here automatically, we can see that transition and that correlation between PRBs and frequency. And that basically makes everything easier to make that correlation, analyze what we've received from the management system and translate it into a specific frequency. With that, I'm going to be going into the next section, letting Dan go through these quick PIM detection demo. So I'm just going to play it for you, Dan.
Yeah, go ahead. So guys, this is a video I took just because we wanted to make sure I didn't do a live one because we're all traveling right now. So what we're showing here is a CIPRI signal on a system that I have set up with a PRB table at the bottom, 10 megahertz system with my 100 or 50 PRBs. You can do the math. And then we're showing the piece that Eduardo talked about where we are going to inject a quick CW tone. So for the gentleman who asked the question about our IM3, this is what I was talking about, is we have the ability to inject a tone anywhere. And if we use the PRB table, I just did it at the edge, but we use discrete frequencies, so we can actually do it even in the guard band. So injecting a tone and then just moving it, I'm using 1 megahertz steps to show you that, hey, we can show you here to isolate out this carrier happens to be a PCS carrier. That's what I have in my system. But if you were in a vendor that has 3 carriers or 4 carriers or 2 carriers on site, which every service provider does right about now, it helps you isolate which PRB it is. So if you're injecting a tone, or if you're fighting an external interference and it's the CW tone, this wouldn't be me injecting it, but it would show up here in the map as it would in heat maps that service providers have as well. But it's just a real quick way for us to show you that it's a very simple test that allows you to control it, your environment, to set it up, to inject it. And then once you know you're on, in this case, PCS sector, go into your system and we analyze all 4 antennas simultaneously, all 4 branches. I should be careful how I say that, antennas are different. All 4 branches simultaneously monitor the RSSI, some people call it RTWP, uplink noise value is really what it is, as well as the slope. And I've tweaked my slope a little bit because this is a PCS example. I wanted it to turn red. And look for that PIM product, right? In this case, my example here is PIM on a single sector, which would be indicative of an internal PIM problem. But in all fairness to everyone on the phone call, this is an external PIM problem, but I have 3 50 ohm loads and a single antenna in my lab setup. Therefore, it only ever shows up once. But it's very simple. Once we have the system configured, you go into either a single antenna view, a dual antenna view. Most people go right for the quad view, since 99% of our systems are 4x4 MIMO right now. But we still have a lot of DAS systems, which are 2x2 MIMO, so we fully support that. Overlay the antennas, allow us to view them right on the screen, add pass-fail limits, and then we immediately jump to our next guest speaker, because he's going to talk about the process. But we wanted you to just see what it looks like in a live setting, right? Eduardo, anything else you'd like to add to that?
No, thank you, Dan.
Or Tom.
Yeah. Appreciate it. Now this last section, it's going to be about how, okay, so we have found a problem. We have found a PIM problem, how that can be mitigated, how can that be resolved. And here we have the pleasure to have Tom with us, and he's going to be helping us with the best practices. Tom?
All right, great. Thanks, Eduardo. Appreciate that. I want to start with a little background on ConcealFab. We are a Valmont company that is primarily in the business of making concealments, hence the name ConcealFab. But we've also been working since 2016 to develop solutions to mitigate external passive intermodulation. Our primary goal is to, develop and sell products to fix the problems that are commonly occurring at cell sites. But we found out very early in the process that if you want to sell products to fix PIM, you have to have trained crews out there that can accurately locate where the PIM's coming from at the site. So for that reason, we've become heavily involved in the test and measurement side of the business. All right, next slide. All right, so this flow chart, the part I'm showing right now, I'm calling it the original process, but it's not really the original process. This is what we evolved to after several years of doing this testing in the field. And, it begins with an operator experiencing elevated noise. And the KPI that usually is the one pointing this out is either RSSI or RTWP, as Dan mentioned. And the next logical step is to send somebody to crew to the site to determine what the problem is. And what we've learned very quickly is that there are common sources of passive intermodulation at cell sites that you don't need test equipment to find. We found out over and over that loose metal-metal contact and galvanic corrosion close to the antenna can create service impacting PIM. And so what we recommend doing is if you get to the site, perform this process called PIM hygiene, which means that you remove, repair, or replace these common sources that we've over time have learned are going to be problems at the site. And on the replacement side, ConcealFab has developed a pretty wide portfolio of cable support solutions to replace the PIM-prone versions that are often found at sites. The next step in the process is, after performing PIM hygiene, test the site. Now, when I say test, what I'm referring to is go back in, connect the radios, and then go back and monitor your uplink noise levels to say, is the site now passing? And in some cases, hygiene enough is going to find the problems and repair it. If you still have elevated noise, the original process said to send the crew with a PIM analyzer and use the PIM analyzer to excite the PIM sources. So when a PIM analyzer is used, you disconnect the jumper cables from the radio, you connect the PIM analyzer, you inject two frequencies, two CW tones into the system under test, and you monitor the magnitude of the third order intermodulation product that's generated by those test signals. We use a feature of the PIM analyzer called distance to PIM to give us an indication of where the PIM is coming from. We can use a PIM probe to go hunt that signal outside the antenna system. Distance to PIM will tell you if it's an internal problem, and you can usually fix those by either replacing a jumper or applying correct torque or cleaning connectors, or in some cases, replacing the antenna itself. If it's an external source, sometimes you can fix those too. Sometimes the external sources you find may be some hygiene that you missed. It may be something that wasn't obvious, but the PIM probe will identify that. And in many cases, particularly on a rooftop site, you'll have things like parapet walls out in front of the antenna. And while you're there doing the investigation, you're not going to fix that, but you do want to know what would be the benefit if I did come back later with a permanent solution. And so in that instance, you would cover the parapet wall with either a PIM blanket or a PIM foil material. Here again, more products that ConcealFab has developed to support the testing process. And look for how much improvement I would get if I came back later and did a permanent repair. So the PIM analyzer piece of this is an iterative process. You start with a high level of IM3, and every time you improve it, you're making steps, and you work your way down until you get to a level where you think the linearity, i.e. the third order intermodulation product, is at a low enough level that the site's going to pass. And so then we reconnect the radio to the system and test it and say, have we fixed the noise rise problem? If the answer is yes, then usually if you want to get paid, you're going to have to create some kind of report to describe what you did. And if it's still failing, which can happen, it doesn't, we're not always going to be able to fix everything. For instance, if there are power lines out in front of the site, or the antenna is shooting, it's on a building and there's an adjacent building close by, and somebody's barbecue on the balcony across the street is a PIM source, we're not going to fix those, but we can collect enough data during the process in order to provide the operator with an explanation of, we got this far, we couldn't go any further because of whatever the remaining problems are. So a couple of pros and cons. Pros are the process works. This took some time to develop, but it's a very good process. We have outstanding signal to noise ratio on the CW tone that we are hunting. Which means that we choose frequencies to put that third order intermod that we're hunting into a guard band frequency, and it's a very strong signal for us to hunt and detect. The cons of this is that sometimes it's too good of a signal, and that we may spend time on the sector fixing PIM, reducing PIM, improving the linearity of things that may or may not actually be improving the performance of the sector. And the reason there is that IM3 is it's representative. It's giving us an indication of what the noise level is, but they're not one-to-one. We're testing either one or two ports at a time. We're injecting CW tones in versus the actual system is using broadband signals. the actual site is being affected by multiple sectors in some cases. It could be multiple bands that are combining together. So we're doing an approximation during this process, which, like I said, it's a good process, and but it's not exactly a perfect representation of what the radio is seeing. Okay, hit enter for me, please. So I've now, I'd say probably in the last couple of years, we've modified what we call the original process to show what we're calling an improved process. The improved process doesn't eliminate the use of a PIM analyzer. It just says that we're going to start using a different process and then go back to the PIM analyzer if we feel like we need it. So the improved process, which starts at bubble 1 here, notice that the first 3 steps are exactly the same. You know, you have an elevated noise problem, you send a crew to investigate. The first thing you do is put on your PIM goggles and look for PIM problems, and you either remove or repair or replace them. So those 3 steps don't change. What does change is that before we call the crew with the PIM analyzer, the first thing we should do is let's try to solve the problem by using the site radios to excite the PIM sources. And what we found is that CIPRI analyzers actually speed up that process. Now, you could have somebody, you know, calling back to run commands and give you real-time RSSIs, but real-time isn't really real-time. It usually means that you do something and you're waiting 5 or 10 minutes to get a response. Versus the thing that's really powerful about the CIPRI analyzer is I do something and immediately I see what the impact is going to be on the uplink. And it even allows you to do it multiple times just to make absolutely sure that, okay, I covered this thing and I saw 5 dB of improvement. Well, let me uncover it and cover it back up again. And this is truly real time on giving you feedback on you know what's going on, you know, whether you're making progress with the things that you're doing. Now, one thing we don't have in this case when we're using the radios and looking at magnitude using a CIPRI analyzer is we no longer have that distance to PIM feature from the PIM analyzer. Now, distance to PIM is not perfect, but it does a good job of saying, hey, you need to be looking 10 meters in front of the antenna versus, you know, if it's off the sector and it comes back saying the problem is 100 meters away, well, you know, you can keep covering things on the sector all day long. You're not going to find it if it's off the sector. So what ConcealFab has done here is we've created another product, which we call the absorber kit system, which we'll talk about more in the next slide, that is useful during the hunting process when you're using the radios to be able to first isolate the antenna from its environment to determine if it's an internal problem or an external problem. And then by removing components of the system one at a time, we can get an idea of, well, is it in front? Is it to the right? Is it to the left? Or is it behind the antenna? So that's very, very helpful in guiding whoever is out there to get an idea of, you know, where is the problem? You know, what direction is the problem we're looking for? And then here again, you still use the PIM foils and blankets and such to cover the PIM sources to look to see what is the benefit. And then here again, this is also an iterative process. The good news here is that while you're doing this, you're testing all ports at the same time. And so it's not a you know, test port 1, then test port 2, then test port 3. All 4 ports of that MIMO radio are being activated at the same time, and you're able to actually see all 4 ports at the same time. So when you finish, you either do the same thing, document the repairs. If you just can't figure it out or things just aren't looking like what you expect them to do, that's the point to come back in and use the PIM analyzer. So I think the major takeaway from this is that, you know, it's not one versus another. It's not, you know, one test of equipment manufacturer versus another here. These are all excellent tools in the tool bag, and if you use them effectively, they will help you using them, you know, where they should be used in order to mitigate PIM at sites. All right, next slide. All right, so I talked about the absorber kit, and this is a graphical picture of what it looks like. The kit itself contains 3 components. There's the front absorber kit, there's the side PIM blanket, and there's the rear absorber kit. And effectively what this does is it isolates the antenna from the environment in a way that minimizes the reflections that are being created. And it's also designed to minimize PIM being generated within the foam or within the components that we're putting in front of the antenna. As I said before, if you isolate the antenna like this, and the noise rise is still there, well, then you have an internal PIM problem. If you isolate this and the noise goes away, it's pretty obvious that the problem you're looking for is somewhere beyond the antenna. And then, as I said, you can remove these components one at a time, either to determine where the PIM source is looking, where it's coming from. So if I've completely covered the system, the PIM has gone away or the noise rise has gone away, and I remove that rear absorber foam and it comes back, well, guess what? You're looking for a PIM source that's behind the antenna. So that's more or less how this system is used. Next slide. And this slide is really just in here to show what it looks like. Instead of it being just the graphic picture, this shows the PIM, the absorber kit system actually installed on an operator's antenna. So on the left, you can see the front absorber kit attached, and on the right-hand side, you can see the PIM blanket draped along over the top and down either side, and the rear absorber kit pads slid between the back of the antenna and the antenna mounting pipe. Next. All right, so let's go back. And so this is, I think everything Eduardo was talking about is really interesting, but to me, it really comes down to how do I use this tool in the field to solve the problem? So, connectivity is very important, but once you get it on the screen, now it's a tool I can use to go solve problems. And what I'm looking at is for each of the antenna branches, it's going to display an RSSI number. Now, that number is not exactly the same number as what you're going to get off of the radio system, but what you're looking for is deltas. You're looking for relative changes. So in this case, if we look at the before side and look at the 4 branches 0 through 3 and look at what the beginning level was, and then if I do something like cover the parapet wall in front of an antenna with our PIM foil material, and you look at the delta, that delta is what's important. And what it says is that, I've put a temporary solution on here by way of the foil, and it gave me, better than 10 dB of improvement. And, that might be good enough. I'm sure there's more PIM there we could find. I'm sure we could coat the entire roof in front of that antenna with PIM foil. But, if 10 dB gets you to the point where you've fixed enough of the problem that it's going to improve your customer impact, then stop. So anyway, here again, I love the tool. It's very visual. It's immediate feedback, and you can get an idea of what the actual performance change is going to be based by looking at the difference in the RSSI value that's displayed before and after you've made some change. Next. All right, so to this point, we've been talking about the temporary solutions that ConcealFab provides to be used during the test and measurement process. Well, what is a permanent way of fixing it? And I have a couple of products here from ConcealFab that I want to talk about. The first 2 are what I call my liquid solutions, which means that whatever area you covered with the blanket or with the foil, you could come back and coat with our PIM Shield paint material, or in localized applications where you need to fill a gap or apply it to a poor connection between 2 pieces of metal, we have our caulk product. When cured, these provide greater than 10 dB of one-way attenuation in a single coat. So what we do typically recommend is that when you're using the paint, you apply 2 coats in order to get on the order of 17 dB one-way attenuation, which, if it's a third order intermodulation problem, you're going to see a multiple of at least 3 times that as far as the benefit in the reduction, because you're preventing the energy from getting to the PIM source. It produces less PIM, and then whatever PIM is generated has to now conduct through whatever you've covered it with. So these coatings are very, very effective. It's not just conductive paint. We spent years working with chemists to come up with a solution that's not only conductive, but it's also elastic, so that when you're putting this thing on roofing surfaces or pieces of metal that are going to expand and contract, this material is designed to be elastic as well, so that over time it's not going to stress itself and start creating cracks that now create new PIM problems. Another product we have is our PIM Shield tape. This is typically intended for a localized application. You peel it and you stick it directly to the surface you want to cover. A lot of time, if I have gaps between flashing, this works great. Or if I have things that I just don't have a quick and easy other way of fixing it, I can wrap it in PIM tape and prevent the RF from getting to whatever the PIM source is that's underneath. Okay, next. And so here is that same sector that we had just looked at the picture before. When the PIM foil was in place, we got north of 10 dB of reduction according to looking at the CIPRI analyzer. And then this is actual data from the operator showing that after the application of the PIM paint, we got on the order of 10 dB of improvement. So it's really great that what you see in deltas of dBs on the CIPRI analyzer really does often correlate very well to the level of improvements you're going to get if you do the investment in doing a permanent repair. Okay, next slide. All right, so this is the last slide I have, and I just want to point this out that we, ConcealFab, have just published a white paper. I think it's actually an application note, but it is on our website. The link is here. I think we said that the PDF of this was going to be made available, so you can get it there. I'll also go into the chat and copy and paste the link there so you can access this. But you don't want to just take PIM paint out and randomly put it on roof surfaces. That's just not going to work. You need to be careful in making sure that, well, first of all, make sure the owner of the roof is going to give the operator approval to do this. But then it's important to clean the surface correctly. It's important to put the right primer down in order to guarantee adhesion. Then we do recommend 2 application coats of the PIM paint in order to get the right level of attenuation. And then it's very important to have a top coat on top of that. This site is in Reno, Nevada, and it was a huge difference in temperature between once we applied a black surface onto that rooftop. We had a digital thermometer with us, and I think it immediately jumped to 147 degrees Fahrenheit. And then by covering it with the white reflective acrylic top coat, it immediately dropped down to the same temperature as the rest of the roof. So here again, the top coat, the PIM paint itself is UV stable, but you really don't want to create huge hot spots on roofs. And so the application of the reflective layer is really more from keeping the temperature of the rooftop down so that you're not going to upset the people below with heat coming from above them. All right, I think that's it.
Thank you, Tom. And here just to provide everybody additional information, here you can find, as Tom mentioned, there are some reference materials, some application notes that you can find. One of the things that we have done is we have created solution bundles for PIM detection and mitigation. Those bundles basically are the One Advisory 100, with which you can find PIM, and the addition of different components, different parts that Tom mentioned, like the absorbers, or the blankets, or even the PIM probe. All those we have created different bundles depending on the user groups. So with that, we finished this session, and I'm going to be opening up for any questions that you might have.
Exactly. So I'm going to jump in here, guys. This is Dan. We did have a series of questions that came through the chat. I typed as fast as my fingers will let me, so apologize about typos. But let's review those. Let me get them. Tom, there's 1 or 2 in here specifically for you. You've got one that you're going to answer live. I see that. But let's start. So we had a question on the impact of your IM3 test results when PIM testing antenna lands within the normal uplink carrier and there's user traffic. So I interpreted that 2 ways, right? So I answered it twice because I think I answered it wrong the first time. So in our general testing, since we use the carrier, we don't inject IM3s generally. We don't have an issue where we're creating a problem when trying to solve a problem, right? Which is right. Traditional PIM testers would always use the guard band. The only time that doesn't come true is when we are trying to identify the antenna to make sure that whatever we're hunting on is the antenna of choice, or the carrier of choice, I should say, where my demo showed us injecting a CW. That is not an IM3, it's an actual direct tone that we would inject for a series of seconds. So that is the one thing that would move for that question. A great question came up of what about O-RAN, right? Are we going to have the same visibility in O-RAN? And the default answer in production is no, but there's a lot of caveats to that. So for those who aren't familiar with the Open RAN, the O-RAN architecture, when you move to higher speed data, and I'll keep this very quick, higher speed data, CPRI cannot keep up with the amount of user throughput just based on its technology. We're not in this webinar to talk about that, but so when O-RAN came out, they moved to what they call eCPRI, which is not CPRI as we know it. It uses the higher layers of CPRI, but Ethernet as the baseband, or as the transport engine. And there is no more baseband or IQ data being transferred on a live network. Is that going to be fun when we get there? Yes, it will be. We are getting there in some carriers now, but there are a few things that are being worked on, right? The standard does allow for transmissions during test periods of IQ data or baseband data. We have not seen anyone implement that there, but it was written into there as a clause. And then we go back to what some people may remember as BBU emulation. It's now called ODU emulation, where the test set itself can control the radio. We have that in our system. The AXE container piece is not available yet, but it's coming soon for this exact reason, where we can put a radio into a test state to measure uplink noise frequency. So stay tuned. Once we release that, we'll do webinars on the new features, right? We're not quite there yet. And then we have a question here on, are these good on air antennas only? Air, as most people know, is an Ericsson system where they integrate the radio and the antennas into the same physical platform. So there's no foam jumpers, there's no coax. No, we support any CPRI-based radio. So Ericsson, Nokia, Samsung, we don't really care about Huawei here, but keep those out of the mix for other areas. We support them as well. As long as it's CPRI, we support them, because that there's a standard of how they map all that baseband. So great question on that. Question on, are there best practices? Absolutely. We don't really go over those in here, where this was more about the concept, but there is absolutely a list of best practices per antenna or baseband manufacturer, right? Lock down the sites, you don't create alarms, plug in optical tap. We went through some of that in our previous session. But if people are interested in a more formal one, we do have a lot of those written down, generic, because obviously the carriers control that. We do not as a test vendor, right? Tom, I've got one here for you, and I'm sorry about going fast, but we have a lot of good questions. Tom, is there a list of components that cause PIM?
Yeah, and I just replied to that one and put a link to our application note. And it's not really a list. It's here's all the stuff we found that are common sources. But I think the idea here is, once you get an eye for what causes PIM, it's pretty obvious to say, oh, if it's something that can be loose metal-metal contact, that's probably a problem.
Perfect. I believe I read this next question wrong when I answered it, so I apologize. What is the formula for creating the IM3 found during swept PIM test? It's beyond the scope of this class, but what I did answer is there are traditional PIM testers out there that do swept PIM. We are not one of them. We use live PIM, if you will. We use live base stations, but the formula at a high level is simple. Create one static frequency and then sweep the second frequency through, and it will create IM products that said devices can read, right? And Tom will do a much better job answering that. There's a comment about how we no longer use DIN connectors, and is this mostly detected at tower top antennas? I did an answer on that one. You are right. As we move to the 4.3s, connection-based PIM problems have gone down exponentially, which is wonderful. But we still have problems at bad ports, bad antennas, bad radios, bad coax. And honestly, a lot of our testing is verifying internal for external from a contractor point of view. I want to get paid, yes or no, versus fighting an external interferer, which is, another problem which either gets funded either a different way, but the testing is still relevant for everything. It's just a different way of looking at it. And you're right, a lot better. So, Tom, we have one here. Any idea why in the last 8 months we're getting fluctuating readings when using the absorber kits?
Yeah, I replied to that too. No is the short answer. There's too many things that can cause fluctuation to be able to say definitively it's one thing versus another. I'm not aware of any issues specifically related to the absorber kit itself, but as I volunteered, get back in touch with me, and if you think there is something wrong with the absorber kit, we can certainly bring it back in the lab and validate for sure that that's not the root cause.
We have 4 more questions that have not been answered, so I'm just going to read them, and the 3 of us will do the best to answer it. What about 3.5 TDD? We know that as a CBRS. In a lot of this 8x8 MIMO next 10 connectors. Will this be supported in the future? That is a really good question. I'll start with my answer. It depends, as always. That's the favorite answer we all want. If the vendor is using CPRI, then technically we support it today, because CPRI will packetize the baseband, put it on the fiber, and I've done this at a few private LTEs and private carriers in the CBRS band. If the carrier or the provider or the vendor is using ORAN or an eCPRI based technology, then that's not supported today, and that would go to this ODU emulation feature we talked about that very quickly answered a few minutes ago. So a lot of that depends on the provider of the equipment. If it's LTE, the odds are it's CPRI, because you don't need eCPRI to carry the amount of user traffic on LTE. The LTE is not a fast enough RF technology to warrant a different backhaul. So depends, right? We have a question here that Tom is answering, and Tom just took the question away, so I can't read it. So Tom, what was that one? Is that worth discussing, or is that an offline question?
Yeah, sorry, I have to unmute. So, well, it was a follow-on to the variation question, really, and it was saying, hey, we're wrapping the antenna. We're starting off with a neg 133, and we're wrapping it, and we'll get a neg 118. Then we'll wrap it again and get a neg 113. And my question was, when you say wrap, let's just make absolutely sure that we're not talking about wrapping the antenna in a PIM blanket, and instead are talking about the application of the absorber kit, because if you wrap an antenna with a PIM blanket, you're creating massive amounts of reflections that are shooting all that energy back into PIM sources inside the antenna system that may or may not actually be service affecting. So the absorber kit it's imperative that you use the kit the way it's designed, so that you are not generating high reflections. But here again, anytime you have wrapped it, remember, let's assume that we are using the absorber kit in this case. You are still creating more energy going back into the antenna system. And so if you hit a jumper cable during that process and it's an internal issue, it's going to vary. So it's just like if I use the PIM analyzer and do a tap test, if I've got this thing, fully wrapped and using the correct absorber kit system, and I hit a jumper or wiggle a jumper, and if that's the problem, yeah, you're going to see it jump all over the place. It's very, very reactive that way.
And our last question, does the gear help with proximity issues? I'm not sure I know how to answer that one off the top of my head. The gear help with proximity issues. Oh, and just to be clear, proximity as in design questions where maybe 2 antennas are put too close together and they're within the near field. I want to make sure we get it. Tom and Eduardo, please jump in. I'm not sure I know how to answer that one.
Yeah, and I'm not, and I guess if we're talking about the absorber kit system, yes, I guess is the short answer. That if I'm able to isolate it from the adjacent antenna, you're gonna see that. Now, proximity being an active interference issue from one to the other, you may or may not do the same things to fix the problem, but it's certainly going to give you the isolation if that's what you're trying to look for.
Yeah. And that's a good point, Tom. So one of the keys, and again, I don't have a live system to show you, one of the keys of the CIPRI-based analyzer is real instantaneous feedback. And when I say that the video didn't do it justice, we actually have to apply averaging because we get roughly 100 sweeps or so per second. And to see that in real time is immensely too fast. So as you do cover something or wrap it or put down a PIM blanket or do whatever you do for the mitigation side, the analyzer is showing feedback as it's happening. So from an isolation, yeah, it would do that, assuming we're all talking about the same thing. Quite useful for that, right? Almost like I said, in some cases you walk by with keys in your pocket and you have identified a massive PIM source. And that's when you remember, oh yeah, my training, you don't have keys in your pocket when you run this test, right? And there's one last question, I think, for you, Tom. It looks like another follow-up. I think we should be taking that one offline because I believe we're out of time, by the way. So, that's it for the questions. Eduardo, Tom, Natalie?
Yeah, thank you. Thank you all. And Natalie, you want to close out?
Yes, thank you all for joining. We'll have a report of the Q&A, so you can follow up by email for the open questions, and you will receive a follow-up email also with the recording, with the link to the recording in a few days. Thank you all for joining.
Thank you all.